Okay, so we have another quiz coming up this week. Well, not this week, next week, right? So this is what we did last time. And so again, you guys can speak through your audio if you want to, but up to you guys how you want to communicate with me. So let's start our lesson for today. Now, I do want to mention, if you were doing web work, you might have noticed for section 2.6, I think there's like 1 or 2 questions asking you for integrating factor for an exact equation. So those of you who did that homework, you might have seen it. It's okay if you skip that question because that's not part of the syllabus, but it's on web work. If you want to do it, go ahead and look it up how to do it, but that's not required from you for this course. Okay, so you're welcome to skip that question. I think it's number 8. I'm not sure, but you'll see it's gonna say find the integrating factor to make the equation exact. Okay, so if you encounter something like that, if you want to work on it, work on it. If not, you're welcome to skip it. Okay, so here's our coming up portion for the course. What do we have next week? So coming up, we have our second quiz next class. So that's gonna take place after class. So what's the date for next class? So let me just look it up quickly. Okay, so that's the 16th of June. So this will be June 16th at 7:40 to 8 p.m. So the usual 20 minutes quiz. Okay. So that will be next class. And the sections you are required to know for this quiz are as follows. So sections 2.6, where we study exact equations, and then 2.3, where we did applications, and 2.9, which we're going to cover today. Okay, so that's going to be on our quiz for next class. All right, so any questions about that? So how do you prepare for the quiz? Well, you do your homework, and then you can have extra practice by looking through the recommended question I posted on my website. So you can go over those questions as well. And the solutions to those questions are posted on slater.com. So you can definitely check on yourself. Okay, any questions?
Professor,
Mm-hmm.
for 2.9, right? I was like doing the homework. I think it's the Bernoulli equation one, the substitution.
Right.
So I learned it in a different way for 2.9. So like when I try to do it in like web work, it's like confusing to me.
So I haven't covered 2.9 yet.
Yeah.
So maybe after I finish today's lesson, see if you can do it, right?
Okay.
So on web work, only for 2.9, Sadia, thank you for your comment. If you notice, it only has question for Bernoulli equations. It doesn't have reduction of order for some reason, and it doesn't have miscellaneous questions. So I would say for 2.1, use the recommended questions from our textbook. Okay, so that way you have practice for 2.9. Web work, in my opinion, I don't think it does a good job for 2.9. So if you want to, kind of ignore a couple of those questions, it's okay. Not a big deal for me, but I would encourage you to do the textbook questions definitely for 2.9 to better prepare yourself for the quiz. Okay, so thank you, Sadia, for mentioning that. All right, any other questions? All right. Uh, Okay, so I'm going to go ahead and start where we left off last time. So we stopped. So a lot of you are coming in late. You shouldn't be coming in late. You should come on time, or at least before 6 o'clock. Just letting you know. Right, the class starts at 6, not 6:30. So yeah, be on time. So last time we talked about tank problems. We finished them, and then we started working on compound interest. So we derived formulas. One of them was this. If you have ds dt is equal to the rate times the amount s, then the solution is s of t, which is c times e to the rt, where c could be the initial amount, s naught. Now, if you add a factor k into this formula, then we can have two different scenarios. K could be positive or k could be negative. Okay, so I derived both of these formulas for you last time. If k happens to be positive, then this is our solution, which I boxed on the left side. And if k is negative, then again, you can use the method of integrating factor. You have the solution s of t to be the formula on the right side. And then you can apply initial condition. So let's work through this problem that we didn't finish, but I did write it down. So let me copy and paste. So I hope you guys had some time to think about the question.
It was pretty easy.
Yeah, okay,
It
that's
was.
great. I will do this one, and then I have one more example that I prepared for today. So, okay, so here's the question. So it looks weird because, so just give me a few seconds to set this up. Looks like I have to make it smaller. Okay, so hopefully this is good enough. And then here I have another question that we're going to work through after we finish this problem. So I'll put them more on the bottom. Okay, so let's get started on the first one that we didn't finish last time. So let's call this one example 1. So this is from last time. So Jerry is depositing money into an account continuously at the rate of about 10,000 per year, and the account earns interest of 4% annually, and it is compounded continuously. So we will be using the exponential growth. Jerry begins his first year with 23,000 in the account. Assuming that he doesn't make any withdrawals, how much money is in the account after 3 years? So we just want to set up the formula, and then if you want to use calculator to find the numbers, you could, but that's not going to be needed for this course. So let's set this up. So let's first write down what is given to us. So we have so the rate is 4%, so we're going to be using 0.04. And then what else do we have? We have the K value, right, which is 10,000. Okay, and then he begins his first deposit with 23,000. So you can think of that as the initial amount. He's starting with 23,000. Okay, so we can say S of 0 is equal to 3,000. And we want to know, so he doesn't make any withdrawal, we want to know how much money will he have in 3 years. So we want to know what is the amount in 3 years. So that's the kind of model you want to set up.
Professor?
Yeah?
Is the K a continuous deposit or withdrawal? Is it a continuous thing or is it like a one-time?
So this is how much he takes out every year.
Okay.
Yeah. So just one shot, he's going to take it out.
I mean, so for the K in every problem would be a continuous deposit?
Yes. So in this case, it's going to be deposit.
Okay.
So it's going to be a plus.
Okay. Got it.
Okay. All right. So let's write out the equation. So we're going to be using the model ds dt is equal to r times s plus k, because he's going to be making deposit for 10,000 every year. So you're earning money, right? So that's positive k. If you're withdrawing every year for a certain amount, then we're going to have negative k because you're reducing the amount as time goes by. Okay, so that will be another scenario. So for this one, well, if this is the model we're using, what is the solution to this? So you could memorize it, right? So if I go to our notes from last time, here, if we have this model, rs plus k, then the solution is right here. S of t is equal to negative k over r plus c e to the rt. Or if k is negative, then we have the other formula. So I'm just going to go ahead and copy this because the derivation, I already wrote them for you. You can always go back and revisit. So we have, so you go through the process and you discover that the function that will model this will be negative. Oh, so I'm going to write it this way. C times e to the rt minus k over r. Okay. And now I'm going to go ahead and plug in our initial condition. So, well, what's the initial condition for this one? We have S of 0 is 23,000. So that's going to be 23,000 is equal to C e to the r times 0, well, that's going to minus k over r. So if you want, at this stage, you can start plugging in k and r, but I'm just going to go ahead and derive the final formula and then plug everything in. So what is C? We know C is going to be 23,000 plus k over r. So that's what we're going to substitute into S of t. So I have to move this question further down. Okay. All right. So our formula is going to be now modified using C. So S of t is going to be 23,000 times plus k over r e to the rt minus k over r. Now let's plug in r and k. So we have 23,000 plus, well, we say k is 10,000 over r, that's 0.04. Yep, e to the rt. So r is again 0.04 times t minus k over r. That's 10,000 over 0.04. So that model that will be used for this scenario, asking us to find. We want to know what is the amount when t is equal to 3. So what do you think we have to do to answer the question?
We just substitute 3 into wherever t is.
Yeah, so that will be the answer to this. So we want to know what is S of 3. So that will give us 23,000 plus 10,000 over 0.04 e to the 0.04 times 3 minus 10,000 over 0.04. So that will be our amount after 3 years. Okay, so whatever that number is, that will be the solution. Now, if you want to really check if all of this makes sense, just grab a calculator and plug these numbers in carefully, and you'll see the growth. Okay, so any questions on this problem? So that's the solution to this. So for any interest problem or tank problem, I will just have you set it up, because or if I want you to really calculate the numbers, I'll give you smaller values, so it won't be too much of time consuming. But the idea is know the process, know how to use the formula, know how to plug things in, and understand the problem. What is it asking you to find? Okay. So are there any questions on this? Okay, so if there are no questions, let's work on this problem. So this is the one I typed before class. So let's call this example 2. Okay. So let's read what's going on. So suppose Kat borrows 7,000 to buy a car. The lender charges interest at an annual rate of 10%. Assuming that the interest is compounded continuously and that Kat makes payments continuously at a constant annual rate K. Determine the payment rate K that is required to pay off the loan in 3 years. So I'll give you a few seconds. Think about how you would process this question, which formula you're going to use, and what is given to you. All right, so let's start. So Kat borrows 7,000. Okay, so that's sort of like the initial amount. That's the amount you want to start with, right? So let me write those down. So we are going to okay. So we have the initial amount, 7,000, and the interest is 10%. That's how much the lender is charging. So convert this to a decimal, that's 0.1. And assuming it is compounded continuously, so when we're going to be using the model, ds dt is equal to r times s plus or minus k. And we're going to fix if k is positive or negative. And we want to know, determine the payment amount, payment rate k. So we want to know what is k that is required to pay off the loan in 3 years. So what do you guys think that means? What are we looking for? Okay, so anyone want to try? So Gabriel, what do you think?
Look for look for a case such that when you solve the differential equation, you get s of 3 equals 0.
Right. So we want to know when t is 3, right? Because in 3 years, you want to pay off the entire loan. So you want your balance to be 0 in 3 years. So you want to determine what is the k amount you have to pay every year. Okay, so thank you, Gabriel. Sorry, I picked on you. I'm just going to do them when everyone's quiet. I'm just going to pick random student. That way you guys communicate with me. So I hope you guys don't mind. So we want to know what is K when T is 3 and our amount in 3 years to be 0. That's what we want. So now, what is the K you're going to pick for this differential equation? Is it plus or minus?
It should be plus.
Minus.
So, okay, we have conflict. Some of you think it's plus, some of you think it's minus. Let's justify. How do you know?
We are starting off with 7,000 and we want to get it down to 0. So K would be subtracting away from the loan.
Exactly. Perfect. So ds dt is equal to r times s minus k, because you want to reduce the total amount, right? So you're paying off to someone, so it's a minus k. You're not earning. So thank you. So if I, again, how to solve this differential equation? This is linear. You will be looking for an integrating factor, and you can finish that part. So if you go back to our notes, if k is negative, then this is the differential equation. This is the solution we have. So I'm just going to go ahead and use that instead of deriving. So our function s of t is going to be c e to the rt plus k over r. Okay, and now let's plug in the initial condition. So we have s of 0 is equal to 7,000, which implies 7,000 is equal to c e to the r times 0, that's 1, plus k over r. So that means our constant c is equal to 7,000 minus k over r. So that will modify our model s of t. S of t is going to be c, so c we just computed 7,000 minus k over r e to the rt plus k over r. Now let's plug in what are k and r. So our function s of t simplifies to 7,000 minus k. What k we don't know, right? We're trying to figure that out. R 10%, 0.1, e to the r 0.1 t plus k we don't know, r 0.1. And the next part, so that's the model we're going to be using to answer the question. So we want to know when will the balance be 0? Sorry, we want to know in 3 years, we want the balance to be 0. We want to know what is the k amount he has to pay, right? Or she has to pay. So I think I use cat. Yep. So we want 0 to equal 7,000 minus k. We're looking for over 0.1 e to the 0.1 times 3 plus k over 0.1. So that will give us the k value when the balance will become 0 in 3 years' time. So any questions for this problem? So that's another scenario for compound interest. Okay. All right. So if there are no questions, moving on to section 2.9. So let's start 2.9 with the following. So what are we going to do in section 2.9? So 2.9 it's a pretty interesting section because we're going to be doing reduction of order, and we're going to do some miscellaneous problem, and then we'll study Bernoulli equations. Okay, so 2.9, so you have miscellaneous problem.
Professor, did you say that we could leave our answer like that?
Yeah.
Okay.
Miscellaneous problems, reduction of order. And and Bernoulli equations. So this is 2.9. Now, what are miscellaneous problems? So miscellaneous problems are putting all equations from chapter 2 into one format, and where you have to decide which of the four methods that we learn is applicable to the given differential equations. Okay, so I'm just going to write down a few problems, and you will tell me how you would approach those questions, and that's pretty much it. Okay, so there isn't much to do for miscellaneous, because you just kind of have to decide, is this homogeneous, is this linear, is it exact, or is it separable? So you just have to decide and solve it. So we'll be working more toward reduction of order, because that's a different method, and Bernoulli equation, that's another type of equations that we're going to learn how to solve. So let's consider the following differential equations. So here are some examples. So hopefully you have the four methods memorized. If not, just make sure you go over them before our quiz next time. So suppose you have dy dx is equal to x plus 3y over x minus y. Number 2, 2xy dy is equal to x squared plus 3y squared dx. Number 3, e to the x plus 1 dy dx is equal to y minus y e to the x. And then let me just give you one more. Okay, so here are 4 differential equations. Now, we're not going to solve them. I think you know the methods once you can identify which method, and then just go through the procedure of solving it. So let's identify, just by staring at them, which method out of the 4 we studied that is applicable to the differential equation. So let's look at number 1. So you stare at it and then you think about it. Is it separable? Is it linear? Is it homogeneous? Is it exact? So what do you guys think?
Homogeneous.
Right? So, sorry. Okay. Yeah. So I think it's homogeneous, right? So let's see if we can write this function as a y over x, right? So that's, or you can plug in the substitution k times x and k times y. You should get the original function. So if I were to express this as a function of y over x, I'm going to go ahead and divide everything by x, right? So if I do that, I get the following. So x over x plus 3y over x over x minus y over x. So it looks like, yeah, 1 plus 3 times y over x over 1 minus y over x. So there you go, you have the function of y over x. So homogeneous will be the method to go for this. Any questions on that? So Liana, yep, that's correct. So first one is homogeneous. Now what about the second one? So again, you stare at it for a couple of seconds and you just try to manipulate them and see if you can identify which method is applicable. What do you guys think? So Jay says homogeneous. Anyone else? So Kevin, what do you think? So Carolyn says exact.
I don't think it's homogeneous. The powers don't match.
Okay, so let's check that out. So we have exact and and homogeneous. So let's see. So what I'm going to do, I'm just going to rewrite it and then see if any of the methods work. So let's do it this way. So if I were to divide by 2xy and then divide by dx, I get the following. dy dx is equal to x squared plus 3y squared over 2xy. So I can rewrite it this way, right? So what do you guys think? What can I do from here? Right, so I can divide by x squared, or I can simplify before I do that. So check this out. Because I only have one term on the bottom, I can kind of separate the fractions on top. So we have 1 over, so we get the following. 1 over 2 x over y, so x over y, plus 3 over 2, 3 over 2, and y over x. So I can simplify it before dividing it by x squared. So what do you guys think this equation is?
Never mind. It is homogeneous.
Right, so Sadia, you changed your mind. Good. So it's homogeneous. Liana, yes, that's correct. So if you look at it, we have the function expressed as y over x. So we can say, yes, this is also homogeneous. So this is also homogeneous. And then you know how to proceed from here, okay? What about number 3? Let's play around with number 3. What can we say about number 3? So Suhai Mayu says separable and Carolyn linear and Sadia A separable. Okay, so we have separable and linear. So if we were to use the method linear, you can also use it. Yeah, but I think the quick way to get the solution to this would be separable. Okay, so I'm going to go with separable. Right, so Greg, you're also right, Aisha. If you look at it carefully, we can pseudo factor the right side, and then you have 1 minus e to the x. And then you see the variables, so you can separate them. So you could use linear because it's also linear, but I would say separation of variables will be the easier method. Okay, so this is separable. Okay, and the last one, let's check this one out. So let me know if you guys have questions while we're just going through this. So Liana, yes, so in this case, it happens to be both, right? It's separable and it's linear in y because we can kind of rewrite it. But we wouldn't use the method of integrating factor because it's probably going to be more complicated. So I would go with separation of variables. Now, what about number 4? So number 4, I'm going to rewrite it so that it looks a little better. Multiply both sides by dx. So you have x squared y plus xy minus y times dx plus x squared y minus 2x squared dy equals to 0. Okay, so now it looks like in the form of an exact equation. but we have to check if it is. So Liana says it's exact. Okay, let's check it out, right? So this is the function, we call it m, and this is the function, we call it n. Let's check if their partial derivatives are equal, right? So let's check. So we take partial m respect to y, we get x squared plus x minus 1, right? Yeah. And then we take partial of n respect to x, so that will give us, what will it give us? If I take the partial respect to x, I would get 2xy, right? And then
Minus 4x.
4x. Yeah. So they don't match, right?
It's not exact. You can't use that.
Yeah. So yeah, so not exact. Okay. So okay, that method fails. So now we just have to find another method that should work. What do you guys think?
Linear would work. I believe so. Should work.
Um,
I don't know.
See, I wouldn't go for linear, because if you were to use the method linear, we want to write it this way. We want dy dx plus some function p of x times y is equal to some function q of x, or g of x if I wrote g. And then this is your integrating factor, right? So that will be pretty complicated for this kind of problem. But okay, what do you guys think? Yeah, not sure, right?
Yes.
Is it homogeneous?
Yeah. If you
Let's
divide
check
by
it out, right?
if you divide by x cubed all throughout. Wait.
Mm-hmm.
Wait, no, actually it doesn't work for the negative y. Never mind.
Mm-hmm. Okay. So yeah. So it doesn't look like it's homogeneous. So how can we check if it's homogeneous?
Plug in y is equal to ky and then x is equal to kx and see
Right?
if it gives you the same differential.
Yeah. So you can do that and check, but yeah, I don't think it's homogeneous, because the problem would be when you plug in k times y for y, the third term on the first parenthesis will give us trouble.
Can we use reduction in here?
No, this wouldn't be reduction of order, because you will see how it works.
Oh, okay.
So look like I copied the question wrong, maybe. So I'm going to pause on this question, because it doesn't look like any of these methods it's going to work. So I probably made a typo somewhere. So I'm just going to pause this question. So let's hold on. Okay. So I'll double check my notes and see if there's a mistake in one of these functions, because I meant to give you one of the exact equation, and I thought this was going to be exact, but it's not. So we tested and we see that it's not exact, so it doesn't work. So Gabriel says separation of variables. So it looks like that might work, right? Yeah. So if you keep trying, I think you can do that. So let's try that. So let me just go ahead and write it one more time. So I'm going to rewrite this. So let's factor out the y. So you have x squared plus x minus 1 plus, and then for the second factor, I can take out x squared. So we have y minus 2 dy dx is equal to 0. Yeah, check. It's separable. Yeah, thank you, Gabriel. It's separable. So it didn't happen to be exact, but I intended it to be exact, but oh well, it didn't work. So, okay. So any questions on this? All right, so pretty good. Yeah, this happens to be separable. Yeah. So just yeah, stare at them for extra seconds, I guess. Then the equation will tell you this should be the method to proceed. But every time equation is written this way, I would try exact first quickly because it's easy to check. You're taking partial derivatives. Once it fails, then just run through the list. Is it separation of variables or if it's homogeneous, one of those, okay? All right, so let me give you one more and then we'll start reduction of order. So let's look at the fifth example. Now, what about if you have dy dx is equal to e to the 2x plus 3y? So which method is applicable for this equation?
Yeah, it
So
should be linear.
Liana
It should be
says,
linear.
yeah, right? So y is to the power 1, and then we have the derivative by itself. So it looks like we can write it in the form of a linear function, dy dx minus e to the 2, no, hold on, minus 3y is equal to e to the 2x. So check. We can use the method of integrating factor, right? So this would be linear. And then you would know how to solve this, okay? All right, so by looking at it, you should be able to decide which method is applicable, okay? So those are the miscellaneous questions. So again, the web work doesn't do any of these questions. You're gonna have to look at the textbook questions for a bunch of differential equations of first order where you have to decide which method is applicable to the given equation, okay? All right, so let's move on to how to use reduction of order. Okay, so we're going to do two types of reduction of order. So type 1, let's call type 1 to be the following. So, and we're going to do this more in section chapter 3. So we'll do more in chapter 3. So this method is very useful in the future as well. So type 1, it's going to be where you have equation and the dependent variable is missing. So we'll consider y to be our dependent variable. So type 1 is when the dependent variable is missing. Okay, so that means y is missing. Y is the dependent variable. So you have the equation in the form of y second derivative is a function of the independent variable and the first derivative, where y is missing, okay? So our independent variable could be t or it could be x. So, or you could write it as y double prime is a function of x and y prime, okay? So what's the idea here? So the idea of solving this equation is to come up with a substitution. So we're going to let v be equal to y prime. So that means v prime is going to be y double prime. That's the substitution we're going to be using if the dependent variable is missing, okay? So I will illustrate this using an example. So Let's look at the following example. So say we want to solve t squared y double prime plus 2t y prime minus 1 equals to 0. Assume t is positive. So if you keep in mind, we're given a second order and we want to reduce it to a first order. That's what we call it, the reduction of order. Okay, so we want to reduce second order equation into first order. That's what this substitution will do for us. Okay, so I see that I have y double prime, I have y prime, and my independent variable is t. I'm missing y in the picture, right? So y is not in the picture. That means we have to use the substitution v is equal to y prime. So let's proceed to use this method. So let v be equal to y prime. If I differentiate v respect to t, v prime is going to be y double prime, okay? And we're going to make this following substitution into our original equation. So we have t squared, y double prime will be replaced with v prime, plus 2t, y prime will be replaced with v minus 1 equals to 0. So now what kind of equation is this?
Here.
So right, so it's first order and it's linear. So that means we're going to be using integrating factor to find solution to this. Okay, so that's the idea. We reduce second order to a first order. So if I were to make this in the form of a linear standard form, we divide everything by t squared, and that's okay because t is greater than 0. So then we have the following. We have v prime plus 2 over t v, and I'm going to move 1 to the other side as well. So that's 1 over t squared. So now let's look for the integrating factor mu. So mu of t is going to be e to the integral of 2 times 1 over t dt. So that would be e to the power 2 ln of t. That's t squared. So that means our differential equations above becomes the derivative respect to t of, so I'm just going to write it this way so it simplifies a lot of the writing. So the left side is just mu, which is t squared times v prime, right? So instead of writing d, the derivative symbol d over dt, I'm writing the prime symbol. And on the right side, we have 1. Now we can integrate both sides respect to t. So that will give us, now the differentiation and integration cancels on the left side. We have t squared times v is equal to 1. Integral of 1 would just be a t plus a constant c. Now, because you're doing second order, initially that's the equation you started with, we have to have 2 constants in our solution, okay? So I'm going to go ahead and call this one C1. Or you can put C, D, A, B, whichever constant you like, but I'm going to keep it C1, and the second constant I'll label as C2, but up to you how you want to label your constants. Now the next thing would be to solve for function v, so I divide both sides by t squared, so v is equal to 1 over t plus c1 t to the negative 2. So we were able to successfully solve for v. Well, what is v? Initially, what is v? V was y prime. So let's substitute v is y prime. So we have y prime is equal to 1 over plus c1 t to the negative 2. Now, how do you solve for y from y prime?
Integrate both sides.
Right. Yep, absolutely. So we integrate both sides respect to t. So that will give us the solution where after y is equal to integral of 1 over t, that's ln of t, and then integral of c1, t to the negative 2, that will just be, so another constant c1, so I can just say plus c1 times t to the negative 1 plus another constant c2. That's the integration constant. So that will be our solution to this. So
Professor,
any
should it be
questions for?
negative C1
Um,
times the negative 1?
right, so if you think about it, this part right here, we should have negative c1 because of the integration, right? But negative c1, positive c1, they're just constant, right? So you can just put constant c1. Do you agree?
Yes.
Yeah, so that's why I ignored the negative sign and I kept positive c. Why not, right? Keep the constants positive.
But would
So
it be
any
wrong
questions
if we
on?
said negative?
It wouldn't be wrong, but you probably won't see it as your one of your answer choice.
Okay.
Professor,
Okay. So uh-huh.
if we had it in third order, it would be three constants.
Yes, absolutely. Mm-hmm. All right, so that's second order differential equations where you're missing the dependent variable y, and this would be the method to approach this kind of problem. Okay,
One more
now
question.
let's look. Go ahead.
The original equation that you gave us, it was second order and linear.
So it's yep, it's second order linear,
Okay.
and we're missing the dependent variable y.
Okay.
Yeah. Okay. So this is the first type of reduction of order. Now let's look at the second type. So let's look at type 2 of reduction of order. So type 2 is when you're missing the independent variable. Okay, so we're missing the independent variable. Our independent variable could be x or it could be t. Okay, so they're removed from the picture, or you're removed from the equation. So you'll have an equation of the form y double prime is a function of y and y prime. So you're missing the independent variable x or t. So what is the idea in this case? So the idea for this particular equation is to again come up with the substitution v. So we'll pick v to be y prime, just like before, but we're going to be doing some rewriting, okay? So if v is equal to y prime, suppose you're working with the independent variable t. So t is missing from the picture. So that means I can rewrite y prime. Well, y prime is just dy dt. That's another derivative notation, right? So that means, what is v prime? Well, v prime will be then y double prime. Well, what does it mean to be v prime in a different notation? V prime just means it's the derivative of v respect to t, right? Now, what if I want to rewrite this using chain rule from calculus? So I'm going to write dv dt as dv dy times dy dt, which is same as dv dt, right? So I just introduce the variable dy in the middle. So that, but then here I can make another clever substitution. What is dy dt from above?
It's just
So
V.
right, so that's just v. So I'm gonna make that following substitution. I'm gonna say, well, I can rewrite my second derivative as dv dy times v. So that's gonna be replacing the second derivative. So these are the two substitution we're going to make. V is going to replace y prime, but v prime, which we rewrote it as v dv dy, that's going to be replacing y double prime. So the idea is coming from calculus 3 chain rule. Okay? Let's look at an example. How do you apply this? So here's an example to illustrate this idea. So suppose we want to solve the following: y times y double prime plus y prime square is equal to 0. So do you agree that your independent variable is missing? Right? So there is no t or x in the picture. So we're going to be using this magical substitution that will help us to find the solution. Okay? So this is again reduction of order. So we're going to so again, let me know if you guys have any questions. So because our independent variable is missing, we let v to be y prime, and then v prime, it's going to be, what is v prime? That's y double prime, but we know how to rewrite that. That's going to be dv dy times v. That's where it's going to replace y double prime. So let's do that. So we have y times y double prime. Well, y double prime is replacing with v times dv dy plus y prime. Y prime is replacing with v square equals to 0. Okay, now how do you solve this equation? So we have a first order, right? We want to determine how can we solve this. So let me simplify it, right? So I'm going to divide both sides by v. So we have y dv dy plus v equals to 0. So let's see, what do you guys think? So, right, so this becomes a linear equation, right? But there's also another way you can solve this.
You separable?
Yep, this is absolutely separable. So if an equation is separable, I would go ahead with separation of variables because it's just simpler, right? Sometimes one way is easier than the other. So I'm going to go ahead and use separation of variable. So we have, so let's isolate the variables. So if I were to isolate them, we have 1 over v dv is equal to negative 1 over y dy. So this is separable. Okay, now that I have successfully separated the variables carefully, I can go ahead and integrate them. So on the left side, we have ln of v. On the right side, we have negative ln of y plus a constant c1. Okay. Well, here we can bring back what is v, right? So we said v was, what was v? V was y prime. So let's plug in. So we said v was y prime. And y prime, you can also rewrite it as dy dt, just a different notation. So I'm going to replace that into v. So, well, before that, can I solve for v from here? How do we solve for v?
You have to do e to both sides.
Right, so if we exponentiate both sides, we have v is equal to, so on the right side, it's going to be c1 times y to the negative 1, which is just c1 over y. So that's what v is. And now I can plug in v is y prime. So v is y prime. So instead of using y prime, I'm going to use dy dt notation. It's just you'll see y. C1 over y. So from here, how do we find solution to this equation? Which method?
Oh, separable.
Yep, this is separable. So then we separate the variables. We have y dy is equal to c1 dt. And now we finally integrate both sides to find what is the solution to this. So we have 1/2 y squared is equal to c1 t plus, is it t? Yeah. So the independent variable is t, c2. So that's our solution. But now if you want to write it and simplify this, I can multiply both sides by 2. So we have y squared is equal to 2c1t plus 2c2. Again, you have to keep in mind that this is just a constant. This is also just a constant. So again, I can ignore the 2's and just write c1 and c2. So we have y squared is equal to just c1t plus c2. And if you want to go ahead and simplify more, you can take the square root on both sides. So you get plus and minus square root of c1t plus c2. But I think this is good enough. So we will solve for the constant if you're given an initial conditions. Okay, so because this is a second order, to find both constant, you would need 2 initial conditions. So we have our solution to type 2, reduction of order. So any questions on this problem? Okay. All right, so we talked about type 1 and type 2. Now next type of equation that we're going to study is Bernoulli equation. So let me know if you guys have any questions up to here. Okay, so if there are no questions, moving on to Bernoulli equations. So here is the last part of 2.9. Bernoulli equations. So what are Bernoulli equations? So Bernoulli equations are equation in very specific form. Okay, so these are equation of the form. So you have y prime. Did someone have a question?
No, sorry.
Okay, that's all right. So p of t times y is equal to q of t times y to the nth power. So here n is the power, it's not the derivative, okay? So it's only y prime is the derivative. Now, this is the form of a Bernoulli equation. So that means as the equation differ by the power of n, you have a different ways to solve this first order Bernoulli equation. So check this out. If n is 0, what kind of equation do you have? So we have the following. You have y prime plus p of t times y. So n is 0, y to the 0, that's 1, is equal to q of t. Do we know how to solve this?
Yeah, you use the integrating factor for this.
Yeah, right. So if n is 0, then you have something like this, where it could be separable or it could be linear. Okay, So you'll really depend on what is this function q is. If it's 0, then of course it's separable. If it's a function, then you can kind of play around with this. So I would say if this is the case, then it is separable. Could be linear, right? Depending on what q is. Now what if n is 1? What do we have? Then we have the following. We have y prime plus some function p of t times y is equal to q of t times y. If that's the case, then we have a linear equation. Okay, so that means this is definitely going to be linear. So these are the two cases we have seen already, and we know how to solve them. Now, for any other value of n greater than or equal to 2, we're going to use the following substitution because it's going to be a nonlinear equation. Think about it. If n is 2, then you have y squared. Y squared makes a nonlinear. So you'll have a nonlinear Bernoulli equation. So that means we're going to need a substitution to solve this. We will set v equals y to the 1 minus n. That's the magical substitution you use. And what this will do is this will transform the Bernoulli equation into a linear equation. Using the method of integrating factor after making v equals the power 1 minus n.
Professor,
Professor, you were cutting off.
Okay, so let me fix that. Thank you. All right, so I hope it's working now. Let me know if you guys have trouble hearing me. Okay, so let's see what are Bernoulli equations. Let's look at an example. So here's an example. So say we want to solve the following. T squared y prime plus 2t y minus y cubed equals to 0. Is it in the form of a Bernoulli equation? Yeah, right? What is n in this case?
3.
3. So if you want, you can move the y to the third to the right side. So you would have t squared y prime plus 2ty equals y to the third. So then it looks exactly in that form, except y prime is not by itself yet. So we're going to do the simplification a little after. So from here, we can identify n is 3. If n is 3, let's make the following substitution. We let v be equal to y to the 1 minus n, so that will be negative 2. Then what is v prime then? So what is dv dt? That would be negative 2 y to the power negative 3 dy dt, right? You're doing implicit differentiation. And once you take the derivative, you want to solve for y prime because those are the variable we're going to substitute in here. So we're going to substitute y prime, and then if the term y to the negative 2 appears, we're going to make this substitution as well. So let's solve for y prime. What is y prime from the derivative part from dv dt? So we will have negative 1 over 2 y cubed dv dt. So that will be expression for y prime. Again, I'm going to rewrite dv dt as just v prime, so we can simplify our notation. Y prime is just negative 1/2 y to the third v prime. So that's the substitution we're going to make for our original differential equation for y prime. So let's plug those in. So we have t squared times y prime. Well, y prime is negative 1/2 y to the third v prime plus 2t y is equal to, so I already moved y to the third on the right side, so I'll just keep it as it is. Okay, so that's the step we get after we make the substitution and we substitute them into our original equation. Well, now let's simplify this. So if I simplify it, I have negative 1/2 t squared y to the third v plus 2t y equals to y to the third. And now we're going to go ahead and let's see, what can we do? Let's assume y is not 0, okay? So assuming y is not 0, I can divide both sides by y to the third power. So that will give me the following: negative 1/2 t squared v plus, so if I divide by y to the third, we get 2t y to the negative 2 is equal to, well, on the right side, it's just going to be getting 1, right? Because y to the third over y to the third is 1. Now we're going to make another substitution. What is this equal to?
V.
V. So I think I made a typo. Just give me a second. This should be y prime right here. And this is y prime. Sorry, v prime. This is v prime. So I missed the prime notation when I make the substitution for y prime. So y to the negative 2, we're replacing that with v. So we have the following equation: negative 1/2 t squared v prime plus 2t v is equal to 1. And now I want to put this in a standard form of a Bernoulli equation where the derivative function is by itself. So I want to remove negative 1/2 and I want to remove t squared. So I'm going to go ahead and multiply both sides by negative 2. So we have t squared v prime minus 4 v is equal to negative 2. And then the next thing would be to divide by t squared. So we have v prime minus 4 over t v is equal to negative 2 over t squared. Okay, so now that's in a standard form. What kind of equation is this?
The linear equation.
Exactly. So it's linear first order. So this is first order linear. So what did we do? We made the following substitution and we transformed the Bernoulli equation into a linear equation. Well, now we know how to solve this. Gladly we learned 2.1 where we solve linear equations. So we find the integrating factor mu. So mu of t is e to the integral of negative 4 over t dt. So that's e to the negative 4 ln of t. That will be negative t to the negative 4. So then on the left side of our equation above will become the derivative of t to the negative 4 times v. And on the right side, we will have negative 2 t to the, so if I simplify that, what do we get? T to the negative 6. So any questions? So, well, now we want to solve for this function v, so we integrate both sides respect to t. So that will give us t to the negative 4 times v is equal to. So if I integrate the right side, we get, what do we have? So you add 1 to the exponents, right? So that's 2 over 5 t to the negative 5 plus a constant c. And then the last thing would be to divide by t to the fourth. So the function v is equal to 2/5 t to the negative 1 plus c t to the 4. So we finish solving it almost, but what is v initially? V was y to the negative 2. So let's plug that in. So v was y to the negative 2. So let's substitute that. So we have y to the negative 2 is equal to, so I'm just going to make it positive power for t. So we have 2 over 5t plus c t to the fourth. And then how do we solve for y from here? Well, we want to make it positive power, y to the positive 2. So that's y to the positive 2 on the bottom. 2 over 5t plus c t to the fourth. Last thing would be to solve for y. So y would equal plus and minus square root of the reciprocal on the right side. That's 1 over 2/5 t plus c t to the fourth. So that will be the solution to this Bernoulli equation we have. So let me know if you guys have any questions. How do you guys feel?
These type of questions will definitely be time consuming during the exams.
Yeah, right. So you have to practice, right? Know which step to use, know how to do this problem very carefully. And of course, I will consider the timing will be an issue, so I will do my best to give you guys enough time so you can solve them. Okay, so any questions, guys? Any question on these 3 types of equation that you might encounter for section 2.9? So yeah, so that's 2.9. So I'm gonna go ahead and start with, do you guys want to see another example or should we move on? What do you guys think? How do you guys feel?
I think we should do one more.
Sure, let's do another one. So here's another example of Bernoulli equation. So this is our second example. So we want to solve xy prime plus y is equal to negative 7x y squared with the initial condition y of 1 is 9. Okay. So it's a Bernoulli equation, right? You have y prime, and then you can divide both sides by x to identify your function p and q. But I'm just going to go ahead and identify n. So what is n in this case?
It's 2.
So let's go back. Right, it's 2, right? So you have an equation in this form. So n is the power for y on the right side. So we have 7x, that's just a function g. When you divide by x, it becomes negative 7. So n is 2. Okay. So if n is 2, we're going to use the substitution v is equal to y to the power 1 minus n, so that's 1 minus 2 to the negative 1. And then we go ahead and differentiate this. So we have v prime. So instead of writing dv dt, I'm just going to write v prime. V prime is equal to, so differentiate y to the negative 1, that would be negative y to the negative 2 y prime. And then you want to solve for y prime. Y prime, it's going to be negative y squared times v. Okay? And now let's plug these in to our original equation. So we have x times y prime. Well, that's going to be replaced with negative y squared v plus y is equal to negative 7x y squared. And then I'm going to go ahead and divide by y squared. Oh, so I missed the prime notation again. So just be very careful when you guys do that. So I'm not being careful. So now I'm going to go ahead and divide both sides by negative x and y squared. So I have v prime by itself. So we have v prime minus 1 over x, and y over y squared, that's just y to the negative 1, is equal to 7x over x, that's just 7. Negative cancels out. Y squared will also cancel out. So here we have first order linear. So again, we successfully reduced a nonlinear equation into a linear equation. Okay? And now from here, you know how to solve this. This is a linear equation. But before we do that, we need to replace what is y to the negative 1, because everything has to be transformed into v and v prime. So y prime is this guy. Y to the negative 1 is this term. So if I make the following substitution, then I have a first order linear equation. So v prime minus 1 over x, v is equal to 7. So maybe I should hold on to this and bring it right here. Aha. So we're going to solve this by computing integrating factor mu. So mu of x is equal to e to the integral of negative 1 over x dx. Question? All right, so I'm guessing no. E to the negative ln of x, that's x to the negative 1 power. So that's mu. So that means our
Wait, Professor,
differential equation. Go ahead.
wouldn't separable be easier in this case since we have a constant? Or does it matter?
I wouldn't use separation of variables for this one because it's in the setup of a linear equation. If
Oh,
you
wait,
were to use separation, right?
sorry, I got it mixed up. I just realized
Okay,
you can't factor out the v on the other side. Sorry.
right, because we have dv dt dx on the left side. Yeah. Okay, so if I transform the previous step, v prime minus 1 over x v equals 7, we have v times the integrating factor x to the negative 1. The derivative is equal to 7 times x to the negative 1. And now we can integrate both sides respect to x. So we have v times x to the negative 1 equals 7 times x to the negative 1. Well, that's just 7 ln of x, right? So, yeah, 7 ln of x plus c. And then v would be then 7 x ln of x plus c times x. But what is v? We said v is y to the negative 1. So v initially, we made the substitution y to the negative 1. So we have y to the negative 1, which I can again write it as 1 over y, right? To make it positive power. 7x ln of x plus c times x. And then that means y is going to be the reciprocal on the right side. 1 over 7x ln of x plus c times x. So we successfully finished solving the equation, but this is an initial value problem, right? You have an initial condition, y of 1 is 9, so I'm going to plug that in. Y of 1 is 9, so that would give us 9 is equal to 1 over 7 times 1. ln of 1 is 0, so this term actually goes to 0. So this is 0.
Can you scroll up a
And
little?
then, yeah. So ln of 1 is 0. So then we have 0 plus c times 1. That's just c, which means c is equal to 1 over 9. Oh, that's pretty. Okay. So that means our solution to the initial value problem would be y equals 1 over 7x ln of x plus 1 over 9 times x. That would be our final solution. So any questions, guys? So there we have another problem for Bernoulli equation. Okay. All right, so that's the end of chapter 2. We studied first order and we saw a little bit of second order, but we were able to reduce them to the first order and use the method that we studied and come up with solutions. So that was pretty cool. Any questions?
Professor, for the quiz, how many questions are we having?
I haven't decided. So because this time you might have to compute solution, I might reduce the number of questions.
Okay.
Or if I have you just write out the methods, then I will give you same amount of questions because that way you don't have to solve them. Okay, so I'll probably give you one solving and the rest would just be kind of talking through the question.
Okay.
Okay. All right, so but again, I will give you enough time based on my judgment on how much time it takes me to take the quiz, and I will double that time for you guys. Okay, so that I think that's reasonable. All right, so any other questions?
Yes, if you have a second. I have a quick question about one of your comments on the homework. When it comes to WebWorks 2.9, do you want us to at least attempt it before we just go to the book problems, or do you want us to hit the 80% on that as well?
So for 2.9, yeah, I wouldn't stress about hitting 80% on that, but do the Bernoulli equations, okay? And then I think there's like the last few are a little tricky the way they word it, but you can still do them. But I would say do few on WebWork and then the rest go to the textbook question. They're great. I love those questions.
Okay, great. Thank you.
All right. So yeah, so that's your quiz, 2.6, 2.3, and 2.9, everything we did today. Okay. So for the next 10 minutes, I am going to start chapter 3, just a brief intro to where we're heading next week. So we finished solving first order. Now we're heading to second order. So we'll be solving second order linear differential equations. So let's start with chapter 3. So chapter 3 is more exciting because you will have more ideas on how to solve second order differential equations. So it's going to be second order linear differential equation. So we'll start with 3.1. Section 3.1, you have homogeneous differential equations with constant coefficients. Okay. So in this chapter, the definition of homogeneous is not the same definition we had homogeneous for first order. First order homogeneous means if you're able to express the first derivative as a function of y over x. That's first order. From now on, chapter 3 and on, homogeneous means the following. So suppose we have a second order of this form. So form of second order differential equation. So you'll have d squared y over dx. Well, let's use t. T is nice. And you have the second derivative as a function of independent variable t, dependent variable y, and the derivative y prime. Okay, where f is some function. Now, your independent variable could be x or t. Okay, so second order linear ODE is going to have the following form. You'll have y double prime plus a function of t times y prime plus a function of t times y is equal to a function g of t. So this is called a standard form of second order linear differential equation. So I abbreviated all of that. SOLDE, second order linear differential equation. Now, sometimes the second order can also be expressed in this form where you have a function, say p of t. So let me just write my notation in a different way. So let's say big P of t. Okay, so you have big P of t times y double prime plus q of t times y prime plus r of t times y is equal to g of t. So you could also be given second order linear differential equation in this form. Now if you divide both sides of the equation by p of t, then you get the standard form, which is this one right here. So the one above where the second derivative is alone, the coefficient is only one, and we call this the standard form. Okay, so I would stick to the standard form all the time. So this is just a nice way of expressing second order differential equation. So again, this is just introducing notation, so you're familiar with how to express this equation. Now, when do we call this equation homogeneous? So here's a definition of homogeneous. So if g of t, the big G of t in the second form, or the little g of t in the first form, which I'm calling standard form, is 0 for all t, all values of t, then the equation is called standard form. Sorry, homogeneous. So from chapter 3 to onward, homogeneous means when the right side is equal to 0, meaning the function on the right side, g of t, we're calling it, is equal to 0. So that means we have a function y double prime plus p of t times y prime plus q of t times y equals to 0. That's what it means to be homogeneous. Okay, so these are the homogeneous equations. Now, from this section and up to 3.3, we're going to be working with constant coefficients. So p of t and g of t are constant. So, and if it's not 0, if g of t is non-zero, so here's another thing to keep in mind. If g of t, or the little g of t, is non-zero, then it is called non-homogeneous. Okay, so that's just another term to keep in mind. So here's an example. I'll show you how to solve it maybe next time, but something to think about. How would you solve something like this? Y double prime minus 4, y prime minus plus 3y equals to 0. Okay, so this is a second order linear differential equation with constant coefficient, homogeneous, right? Because the right side is 0, and your coefficients for y, y prime, y double prime, they're all constant, okay? So we're going to take over from here next class. Any questions?
What did you say the difference between the capital G of t and the lowercase g of t was, if there was?
So there's no difference between them. It's just the way I wrote the standard form and the one below, where the coefficient of y double prime is 1. That's the only difference.
Yeah.
Okay, so you could also have your second order expressed in this form, or you could have it expressed in the way I boxed it. The one I wrote it in the box is considered to be a standard form because the coefficient of y double prime is 1. Okay. All right. So any other questions? All right. So the quiz will be on 2.6, 2.4. Didn't we get quiz on 2.4? I thought we did. Hold on. Yes. We did. All right, so 2.6. Okay, so I'm not losing track of what's going on. So 2.4, yeah, we already finished that. So 2.6, 2.3, and 2.9, what we covered today. Chapter 3 is not going to be on the quiz, but I will open up your homework session, but that's going to be due the following weekend, not this weekend. Okay, so this weekend is just 2.6, 2.3, 2.9, and do the recommended question from the textbook. Those are good ones to study for 2.9, okay, especially 2.9. All right, so I will end our session here for today.